הם באמת עושים את הדין הזה פה בעצם?
אני אמרתי להם.
הכיסאות האלה... קצת מפריע. ליאור, בסדר עם בצד הזה?
כן, כל עוד זה לא נכנס למצלמה.
אוקיי, אמרת שעשית לי איזה פרומפטר כזה?
לא, זיו אמר. שנייה, רחלי, אני חייב רגע. רואה שם את ה...
אני רואה average watch time. איזה קטע, אבל יש דיליי אדיר. כי עכשיו ראיתי את...
היוטיוב לוקח לו, הוא יכול להגיע לדיליי של דקה וחצי.
איזה קטע, עכשיו אני מתיישבת. נראה שאני מאוד מרוצה.
אז אנחנו רואים רק את זה, נכון? אז זה לא ידיעה.
מה אתה אמור לראות?
אני שמתי את הטולי פה. שלא יראו אותך, שנוכל את יודעת ל...
כן, אבל יש את ה-time.NL הזה שעשיתי.
אני התחלתי כבר בלייב, כדי שלא יהיה כמו שקרה פעם קודמת, שאנחנו ללחוץ בלייב.
אז עכשיו אתה, לזה תעשה פשוט אדיטינג.
אנחנו כרגע באוויר.
כן. אז רק, אבל יהיה לך לחתוך המון, כי זה שעה ורבע.
היוטיוב לא... את רוצה לקחת אותו, אז... אפשר לעשות את זה.
איפה זאת?
לחתוך
ואין מגבלה של הגודל, כי אז זה עוד יותר גדול עכשיו.
את מה שאנחנו שומרים אצלנו, כאילו את מה שאני מקליט אצלי, אני אחר כך ארוך.
אוקיי.
היוטיוב תוכלי למחוק ברגע שנסיים.
טוב, תגיד לי מה זה.
כן.
תגיד לי כשאתה יכול לדבר.
אפשר.
טוב. האם הזמנתי אותך ב-17, 18, 19 באוגוסט? אני עושה summer school.
ראיתי איזה משהו על זה, אבל לא...
אני עושה 3 ימים summer school. ממש לא הזמנתי. What? Dank je wel. Zeg tot wanneer ben je hier?
Hey, how are you? Yeah, I can see you. I see you too.
Tot wanneer ben je hier?
Tot met dinsdag vol.
Als je dingen voor raar zou doen.
Ja, het gebouw hier is donker. Dat komt de zonwering, het is heet, dus de zonwering is flink om
Leo, you see that Mark is actually very dark. Mark, can you say something so Leo can see you?
Yes, can you hear me?
Ja.
Can-
אנחנו לא יכולים לשפר לו את התאורה.
Waarom? Is er een lamp naast jou of iets?
Ja, ik moet even de zonwering omhoog doen, denk ik. Ik denk dat dat wel
Oké,
helpt.
dan meteen als kan. Ik wacht op die presentation van Richard.
Ja. Even kijken, ik heb Richard net geappt.
Ja.
Eh,
Ik kan het ook doen, maar ik dacht het is nu allemaal via jou gegaan, dus ik laat het.
ja, hij zei dat hij bij mij in het gebouw wil komen zitten. Dus ik denk dat hij any moment hier kan komen. En dan zie ik hem wel.
Ja. Ja, want we houden ervan als we dat van tevoren hebben, alleen maar voor de zekerheid.
Ja, nee, dat snap ik heel goed. Ik heb hem geappt, ik heb nog geen reactie.
Lichting, dan kan men jou beter zien, want zo zie je eruit alsof je meer in het donker zit.
Is het echt zo slecht?
Ja,
Moment.
ik weet niet hoe het eruit ziet. Als je even zit, dan laat ik je zien. Regas, Echt iets?
Ja?
Oké, ik stuur je dat, dan kan je zien hoe het eruit ziet.
Oké. Ik maak even ik doe even de zonwering omhoog. En dan denk ik dat het
Dit
beter
is
zo.
wel goed wat ik zie. Meestal zie je er niet zo uit.
Ja, meestal zit ik... ja, dat is inderdaad erg donker. Meestal zit ik op mijn kamer. Ik ben nu op de universiteit voor het eerst weer in lange tijd. Ik gooi even de zonwering omhoog. Momentje.
Okay.
Beter? Nog niet heel erg, hè?
Nee, het is ietsje beter. Het is vooral van jouw linkerkant dat het zo donker eruit ziet.
Ja.
Misschien als je op links zit, want aan jouw rechterkant. Sorry, als je meer naar jouw rechterkant gaat, want jouw linkerkant is überhaupt donker. De achtergrond is ook donker.
Ja, dat kan ik op zich nog wel wijzigen. Dat maakt natuurlijk wel.
Nee, fysiek, als je meer links zit, dan het ziet er jouw rechterkant ziet er beter uit.
Ja, even kijken hoor.
We hebben
Ik ga even kijken. Dit is waarschijnlijk beter of niet?
Ik zal je laten zien hoe het eruit ziet. Ja. Kan jullie het zeggen?
Ja.
Ja, het is beter. Nee, het is echt goed. Ik laat je het zien, want dan geeft het je ook een beter gevoel. Is het goed.
Dank je.
Ja, wacht eventjes. Oké, kijk maar dat verschil. Stralend.
Ja, beter. Ja, dank je.
Ja.
Ik ga Richard nog even achter de broek zitten en dan moet ik er nu eventjes uit. Ik heb nog één andere meeting en dan ben ik er om 15:15 weer in deze link, oké?
Met Richard dus ook om die testing te doen. Dus ik kan Richard ook zelf schrijven, maar zeg maar wat je wil.
Ik stuur me ook wel een berichtje dat hij ook eventjes in...
Dus dat zou echt helpen, oké? Dat is ook goed voor hem. Geen technische dingen hebben. Dat is wat we eigenlijk dit uur doen. Dus gewoon kijken dat alles goed loopt.
Ik heb Richard 2 berichtjes gestuurd. Ik kijk eventjes of hij reageert. Als hij in een kwartiertje niet reageert, dan bel ik hem wel even op. Ik denk dat hij ook zo in het gebouw komt hier. Dus dan zie ik hem.
En Robert Jan Smits, hoe gaat dat? Is dat Robert Jan Smits of Smits?
Smits. Robert Jan Smits.
Ja, die S. Ik introduceer hem. Ik heb jouw biosketch hier niet bij. Introduceer je jezelf, kan dat? Zal ik eerst Robert Jan Smit introduceren?
Ja, dat lijkt me goed. Als Robert Jan Smit, laten we het zo doen. Als jij begint. Ik typ het nog wel even uit, ik stuur het je nog wel even toe, dan weet je wat ik ga zeggen.
Is goed. Mooi zo. Heb je ook die summer school gezien?
Ja, heb ik gezien, ja. Noem jij die nog even?
Dat doe ik zeker. En we zijn ook van plan, alleen maar dat je dat weet, dat uiteindelijk zal hopelijk een soort van prijs komen voor degene die het beste heeft meegedaan. En wat ik probeer te doen is om een delegatie te organiseren vanuit Israël naar Nederland. Misschien in november. Midden november.
Heel mooi, heel mooi. Oké, Racheli, ik moet nog eventjes hier uitzetten en I'll be back op zijn laatst 9:15.
Is
en
goed.
staat de app gewoon bereikbaar.
Is goed, bedankt.
Oké, tot zo.
Is wat anders doen, laten?
הורדתי. כאילו ברגע שאני מעביר הוא כאילו מנתק אותי, מנתק אותו, זו הכוונה. לא, עליו השארתי. גם ממנו? ואז הוא בעצם לא נוגע לי בכלל בדבר הזה. אוקיי. כן, הנה, אני רואה זה עובד, זה באמת... אוקיי. בסדר גמור. רגע, ומה יום חמישי? עכשיו יש לי זמן. זה עם מדגום, הכל נכון שלם, כן, אני רוצה משם גם שידור וגם פיגור. הייתי מעדיף, שמע, יותר כיף בפסטיבל הג'אז חלוקת תואר דוקטור במכון שלם. לא, אבל בכל מקרה, לא נראה לי שקצת, לא נראה לי... לא, ברור. תודה רבה. פשוט איזה לאוד חדש של הפיניק, חסריין, משחק אחר וגם. פתאום הכל התחיל להשתגע לי ולא גם. יאללה. ביי אריק, תודה. ביי אריק. טוב? מעולה, איך אתה? וואלה. פתחת פה... כן. מאז שהתחלנו להכניס את היוטיוב, אמרתי, זה לא יכול להיות. תעשו, אתה יודע, זה מגיע כבר ללייב.
עובדים אבל שניהם כן.
כן.
מהאדום שניהם, נכון?
שניהם עם האדום, שניהם היו צריכים ריסטארט הבוקר. כאילו, אל תרגיש רע. אני באתי וכאילו היה צריך שוב פעם לכבות להדליק את הכל, ריסטארט למחשב.
כן, הם יוגה, אבל לא... זה העיקר שזה עם האדום שניהם, שזה באמת מוזר שגם הוא לא ידע את זה.
ושניהם עובדים.
כן.
זה מה שחשוב. ביי דו. חשמל את זה?
לא, אנחנו נחליף. אני אטעין את זה.
זה אותו...
כן, זה אותו מחשב. זה די מסוכן שאני לא מביאה איתי את ה...
זה אומץ.
כן? אין לי אומץ. אתה לא נתת לי משהו, הם לא מכניס, אני לא רואה אותם. אתה יכול לעשות שאני יכולה לראות אותם? אבל אני לא רואה, והוא מראה לי. אני בפרטיסיפנט, אני לא רואה שום דבר.
גם אני לא, כולם נותנים.
לא, כי הוא הראה לי הרגע שהוא מנסה להיכנס ואנחנו לא נותנים לו. משהו לא טוב.
אריק עזר לי, אני Thank you, bye-bye.
אז אני לא...
אני גם לא.
אבל הוא מראה לי, please wait, the meeting host will let you in soon.
אז שיחזור ל-waiting room, אולי הוא ייגש להתחכות או משהו. את רואה, ברגע שאני יודע...
לא, אני יודעת.
שהוא יגיע...
Hi. Wil je nog een keer proberen? Want we zien jou nu niet. Is goed. We willen even proberen dat het lukt. Ja. תגיד לו להכניס, כן, אז אני לא רואה אותו. אם אתה ראית אותו עכשיו, אז... אתה רואה אותו?
אותו רק במחשב אחד, זה נקרא. טוב, אבל סבבה, אחי, סבבה, אני אדבר איתך.
אז אני לא רואה אותו.
יאללה, ביי.
אני לא רואה אותו. אתה יכול להכניס אותו? Hi, goedemorgen. Guido? Ik zie je aan de kant, dus ik zie jou alleen maar jou. We zien jou van jouw rechterkant, maar niet van de voorkant.
Ik hoor je nu, ja?
Ja, maar wij zien jou alleen maar van jouw rechterkant. We zien
Ja,
niet
weet ik,
jouw...
maar ik zit straks in een andere kamer. Ik zit hier even wachten.
Goed. Wil je eventjes proberen dat jouw PowerPoint goed werkt?
Kan ontbreken. Ja.
Guido?
Ken. Ja, dat is goed.
Ja.
Hoor jullie ook?
Guido?
Kom maar zo wel, ga er
Volgens mij gaat het goed zo.
Ja, het gaat goed. En, misschien installeer je jezelf dan in die andere kamer en doen we het nog 1 keer. Alleen maar te zien dat alles goed is.
Oh, ja, oké. Nee, maar dat komt goed. Ik bedoel, ik zit nu achter het bureau, daar zit ik in een andere kamer.
Is goed. Oké, tot ziens.
Alright, dankjewel.
Ja, bye bye.
לא, עכשיו עשיתי על זה הוסט במקום אותך.
אוקיי.
שניהם מופיעים לך כרחלי. תראי שעכשיו.
כן, הוא כרגע יצא.
לא, כתוב שם שאת הוסט, ואני שותף.
אין בעיה, הכל בסדר.
רגוע.
יופי שאתה רגוע. מי זה מרגש כזה? עשה לנו עדיין את המצגת של ריטרנד.
Ik zie even naar Racheli dan een.
Dan zit je naar het zoeken.
Die komt eraan. Mijn presentatie die heb ik nu via een link.
Oké.
Ja, dus op een via server. Ik zal het maar bij jou doen. Dan kun je even checken of je goed aankomt. Ja?
Ja.
Nu weg. Ik heb hem rechtstreeks naar Racheli gestuurd.
Oké.
Verder kan ik gewoon mijn screen saven, denk ik. Of share, denk ik.
Dat is wel de bedoeling, ja. Dat is wel het idee.
Even kijken of...
Dat kunnen we nou uittesten. Oh ja, ik zie het. Ik heb je link goed ontvangen. En ik kan er ook bij. Ja. Ja, helemaal prima.
Ja, ik even nog kijken of ik een backgroundje kan doen.
Zit jij aan de overkant, Richard?
Ik zit aan de overkant, ja. Hey, even had je die gezien nog van Pauline? Ik heb er iets teruggestuurd, hè?
Ja, ik zag het.
Ja, het is allemaal, maar dat is dus al op hoog niveau geweest, hè, Mark?
Ja, dat denk ik ook, Richard. Ik denk dat het daarom ook heel goed is dat wij ze voor een fait accompli stellen en niet om toestemming vragen.
Precies. Want ik heb die mail nog eens teruggelezen, maar daaruit lees ik helemaal nog niet die organisatiegraad die ik nu in deze mail teruglees.
Ik ook niet. Goed. We spreken haar maandag wel eventjes.
Nou, we hebben nog geen naam genoemd, dus dat is het goed.
Ja, precies. Ja.
Ja,
goed, even kijken. Jouw presentatie komt goed binnen, heb ik hier. Yes.
Hij staat.
Worden we nog een challenge, Richard?
Nee hoor, dat wordt geen challenge. Nee, want het is maar tot die ene slide, hè? Dus
jij stopt hem daarna. Oké, ja.
Dus het is maar 10 slides, denk ik, of zo.
Oké. Ja, nee, ik dacht
Ik
dat
heb
je
wel helemaal opgestuurd, want ik hou die verzameling hou ik compleet, snap je? Ik zet gewoon alles wat ik niet gebruik. Dus ik heb nu iets van 13 slides.
Oké.
Dat moet wel kunnen, want er staat niet veel op.
מרץ זה הזמן שלנו שמפסיקים. אחרי שתומר עולה, אז אפשר לפתוח את כל אנשים יכולים להיכנס.
יוטיוב אנחנו בלייב, נכון?
יוטיוב, אנחנו, כן, זה כבר עושה, average watch time is 12 דקות. יש שני אנשים נראה לי שאנחנו הרבה יותר זמן, כן?
לא, ה-watch time זה כמה בן אדם נשאר לצפות.
על הדבר הספציפי הזה?
כאילו, על ה-average של בעצם זמן צפייה של...
הבנתי.
לא זמן של...
הבנתי. ומה זה פלייבקס? 7?
מישהו שנתן פלייבק.
מה זה?
לחץ פליי כדי לראות מההתחלה אם יש משהו וזה.
אוקיי.
צריך למצוא לזה משהו יותר...
הבנתי. וזה עדיין על מיוט. לא, פה. זה עדיין על מיוט.
תשמעו, זה אצלך במיוט, זה לא...
אוקיי.
זה כדי שאת לא תשמעי לופ של עצמך דרך הרמקולים.
אני שולחת לך את המצגת של ריצ'רד, זה מצגת מספר 1.
אני לא אקח אותה. אני חושב שהם עובדים על המצגות וזה.
אין בעיה, אז יש אותה.
כן.
שלחתי לך אותה, ואם צריך לי יש אותה.
אנחנו נעשה איזה שליפה... אבל הפעלה בראש.
אני חושב שאנחנו עושים טוב, שתמיד אנחנו מבקשים את זה בראש.
אחד הפרופסורים.
גם אני לא טכנולוגית, לא טכנולוגית.
בסוף היינו צריכים לחלוק אותם, לעשות שרבים.
אני לגמרי יכולה להבין את זה. אני לגמרי יכולה להבין את זה. אני חושבת שזה סקיל שצריך, וכמו שאתה אומר, הוא כל הזמן גם להתקדם. אם אתה רואה את תומר, אז אתה יכול להכניס אותו. אני מתקדם למצגת.
וגם עוד רגע מבטלת כבר...
כן. תמיד אני אוהבת שקודם אנחנו עושים את הטסטים, ואז האנשים אחרים נכנסים לבוא.
כן, שלא יראו את זה.
הוא שולח גם בסורף דרייב, שיש איזשהו דרייב ששם יש את המצגת שלו, אבל אני עוזבת את זה, אנחנו לא צריכים. מצגת מספר 1. אני עוזבת. אתה רוצה לבטל את מצידי תבטל את זה, אבל אני לא רואה שיש אנשים, כן, כי אני... יש אחד שלא, אבל שלי לדעת מתי הוא יעשה את זה.
טוב, מה שתעשי את זה. עכשיו אני משם.
הנה תומר. היי, תומר.
Hi.
Okay. Let's try out your presentation to make sure that everything is working well, and then we're all set.
Okay.
Thanks.
Can you see the presentation?
Yes. Just in presentation mode.
I am in presentation mode. You don't see it in presentation mode?
You have to switch. You have to switch the display settings. Yeah.
Is it better now?
Yeah, it's perfect.
Okay, great. During my presentation, I'll switch in order to present a short movie of a minute, and I'll switch between them.
And 1 second, Leo was trying to say
תומר, אתה
something.
שומע אותי?
שומע.
אוקיי. רק להקפיד שלא יהיה בפרזנטר ויו כשאתה מציג את המצגת.
בסדר גמור.
אוקיי, אתה יכול לצאת מה...
אוקיי.
אפשר לחלוק מסך.
Okay, we start in 10 minutes?
Yeah, 8 minutes.
Okay, let's be precise.
היי ליאור, בוקר טוב. מה?
אני רוצה כשאנשים...
כן. ברור. כן. אתה רוצה שהיוטיוב יפעיל את הסאונד?
היוטיוב מקבל סאונד.
אני לא יודעת, אתה יודע את זה. אתה אמרת לי שצריך איזה משהו.
לא, מה שהתכוונתי זה מיוט אצלי, אני...
הכל בסדר?
בטוח, כן. כן, כן, הוא כותב ש... excellent connection, זה אומר שהוא באוויר.
אוקיי.
אני מתחיל הקלטה. כמה זה מרגיש לי בערך?
עד 1. שעתיים בשביל... מה? של מה?
במקום להקליט.
אוקיי.
את השלב של הגלריה,
כן.
אני שם בסוף.
נכון.
כאילו לצופים ביוטיוב בעצם אני עושה את הקליטה הזו.
תעשה לי תמונה, כאילו קרוב, חסרה לי תמונה. אבל שתצא טובה וזהו, כמו שהיה עשיתם.
מה, פורטרט או...
כן, אין לי כזה. בלי שום עלים, בלי שום דבר.
עם טיפה רקע? יש לנו טיפה, לא, אני אוותר על הדגל, אני משאיר את העניין. ותסתכלי כאילו מעבר לכתות שלי.
Good morning.
Morning, Dr. John.
How you doing?
Morning.
Doing fine.
Good morning.
Good morning.
Remember we met?
Absolutely. How you doing?
I'm doing very well. Thank you so much. Yeah.
What's going on at the moment?
At the moment, things are very quiet here, and due to the vaccination, we can also live a normal life. So that is also very good. And we're working. So another good thing.
There's a lot of cooperation projects going on, eh? Between Holland and Israel, eh? It's in all fields, eh?
Yeah, indeed. Okay. Robert, Leo wants to say something to you.
Sure, yeah.
Hi. Can you please close the curtains behind you so we can see your face, because the camera is...
Okay. I got a beautiful view on the campus. I'm going to take it away now. Oh.
Yeah, it's an amazing view, but it confuses the camera, so...
Is this better or not?
A bit.
Else I change positions if you want. I can sit. If you can't see me properly, you can also sit somewhere else. I'm doing this from my iPad, so
okay.
You can also do it from here. Just sit up.
That's much better.
Is better?
Yeah, much.
Background, which is perhaps no problem if you see the map behind me.
No, we see the map of
a
Europe.
bit of it.
Better over here? No,
I
go back to the position I just had. Yeah.
I think the map was better, yes.
The map was better, yeah.
Good.
לא, פה בצד, איפה שה...
זה אחד מה...
כן, בדיוק. לא, זה פשוט שנייה. אני צריכה להיות אותו באמצע?
You still remember these?
Show me? Yes. You can show them.
I have 5 of them.
Oh, really? The highlight was the celebration of 20 years Israel and the EU.
That was amazing. That was just amazing. Really fantastic celebration. I have such good memories of that.
Yeah.
That's why I've also been pushing so much for the full association of Israel to Horizon Europe. I don't know if you followed that in detail.
Yeah.
I think that since I joined the Israeli Dutch Innovation Council, we've organized now 3 mini-symposia, Racheli, right? In about 4 or 5 months. And they were all very relevant and very well attended, and with a lot of collaborations.
Yeah, we'll start in 1 minute. Is er dan soms aan de mute? Ik ben aan de mute recording. Good morning, Boker Tov, goedemorgen. I welcome you to our Dutch-Israeli mini-symposium on desalination, electrolyzers, and green hydrogen production. We have a wonderful program for this morning, and I would like to start with a few welcome notes. My name is Racheli Kreisberg. I serve as Innovation Attaché, and I work at the Netherlands Embassy in Israel. And I'm part of the Netherlands Innovation Attaché network of the Dutch Ministry of Economy and Climate Policy. At the embassy, we have an economic department, and at the economic department, we have, in addition to innovation, trade and commerce, as well as the NFIA, the Netherlands Foreign Investment Agency. We have also established in November 2016 the Israeli-Dutch Innovation Center, and the Innovation Center, IDIC, has an advisory board. And I'm very privileged to have one of the board members, Dr. Mark Boneschanscher. I am participating today as co-organizer of this mini-symposium. In addition, we have Patrick Kneuven from Heaven in Groningen, also both on the field of energy transition. What we do here at the embassy, and specifically at the economic department in the field of innovation, is to foster R&D collaborations between Israel and the Netherlands. And we do this through different means, and I will share with you a few of those. In the time preceding Corona, we of course did this through missions, and we organized missions from the Netherlands to Israel and vice versa. And we organize pitching events for Dutch startups, for Israeli venture capital, collaborations at the level of the EU projects that are very productive for both sides in order to develop the collaborations. But after Corona, we decided that we need a different means, and we developed a series of Dutch-Israeli mini-symposia. And this symposia is one of this series of activities. Aim of the of these mini-symposia is, of course, to exchange knowledge between the speakers as well as the audience. As you see, we have a Zoom event, but we also have it live on YouTube, and you can later on access it through the live YouTube link that I will share with you. The activities in the field of hydrogen commenced in September 2020. We had a hydrogen course that was co-organized by the Energy Delta Institute of the Netherlands and myself, which attracted 100 participants from Israel, a lot of them from the government as well as from the industry, and we set the baseline for the understanding of the field of hydrogen. Later on, starting from the 13th of January, we have had several Dutch-Israeli mini-symposia focusing on renewable energy conversion and storage, especially with the University of Ben Gurion in the south. We had on the 2nd of February, the first hydrogen mini-symposium, which focused on hydrogen and energy transition. And on the 29th of April, we had a mini-symposium focusing on green hydrogen production and solar energy.
Oh, yeah, maybe it's a small.
What we will focus on today is the combination of Israeli desalination technology, Dutch electrolyzers, and the production of green hydrogen. What are our plans for the future? On the 17th of August, we will invite you to take part at a summer school, a 3-day summer school, with the aim of developing hydrogen valleys. We would like to train people how you set up a hydrogen valley, and this is the objective of our summer school. We will also try to attend the World Hydrogen Congress that will take place in the Netherlands between the 4th and the 6th of October, and hopefully later on this year send a delegation from Israel to the Netherlands to meet the right people and to see how the Netherlands has already established several of its hydrogen valleys. We are now going to start with the opening words of my colleague Robert Jan Smit, and I would like to introduce you with your permission. So first of all, we met in person a couple of years ago when Israel celebrated 20 years participation in the EU framework program. And it was wonderful meeting you then, and I'm very grateful that you are with us today. Robert Jan Smit is the president of the Eindhoven University of Technology. And prior to this, he worked at the European Commission in the positions of Open Access Envoy, and he was the Director General of the DG Research Innovation, where he was responsible for defining and implementing the EU policy and programs in the field of research and innovation. The annual budget for Horizon 2020 was 8 billion euros. And Mr. Smith is also one of the architects of the successor program, Horizon Europe, which we also will use for the establishment of the R&D collaboration between Israel and the Netherlands in the field of hydrogen. The annual budget of Horizon Europe is 10 billion euros. Mr. Smith has several recognitions and awards for his contribution to European science and innovation. He is an honorary member of the Academia Europea and of the Koninklijke Hollandse Maatschappij der Wetenschappen. He has degrees from the University of Utrecht, my hometown, the Institut Universitaire d'Études Internationales in Switzerland, and the Fletcher School of Law Diplomacy in the United States of America. Robert, the floor is yours.
I will first unmute myself and thank you very much for the introduction. And it's great to see so many familiar faces from both countries. Very grateful for this event, a great event, and it comes at an appropriate moment because we are all wrestling with the energy transition. And being now at the Eindhoven University of Technology for 2 years, I'm extremely impressed by this university because it's at the heart of one of the most powerful innovation ecosystems of the world, Brainport. And it's a university which is #1 in all global rankings with regard to cooperation with high-tech industry. So from that point of view, this is an extremely vibrant place. And notably, when we talk about the energy transition, there is a lot of know-how at this university, which will help us to move indeed to a new phase in our energy system. And I think it's great that we can have this Mini-Symposium. I think it's great that we have so many people, expertise around the table to really swap notes and to explore how we can work together, in order to realize the energy transition. And we talk about the energy transition, it's obvious that very quickly green hydrogen comes to the table, electrolyzers come to the table, and many other things. And for that reason, last year, we created at the Eindhoven University of Technology, we created a dedicated research institute called EIRES. And I'm very happy to see that both Professor Richard van der Zande and Mark Boneschanscher are with us, who are leading the institute, which really has a very strong focus on realizing the energy transition. So I'm very grateful to everyone present. I'm very grateful to our mission, the Dutch mission in Israel, for having organized this. And I wish us all a very successful and hands-on event, because at the end of the day, I think the purpose should be, how can we bring the best experts and expertise from both countries together to work on the topics which are so crucial for realizing the energy transition, and not just in our countries, but in Europe and in the whole world, as a matter of fact. I won't talk much longer, but great to see you all, and I wish us all a fantastic Mini-Symposium.
Thank you so much, Robert. And I would like to introduce my colleague, Dr. Mark Boneschanscher, who is the Managing Director of the Eindhoven Institute for Renewable Energy Systems, which Robert just introduced. And Mark is actively involved in setting up both scientific as well as public-private collaborations at EIRES. Mark?
Thank you for your kind introduction, Racheli. Yes, like Robert-Jan mentioned, EIRES was launched last year to bring together all researchers from the Eindhoven University of Technology that work on energy storage and energy conversion from component level to system integration level. And in line with the philosophy of the Brainport region where we are located, there is a strong collaboration that we have with the manufacturing industry in the region. And we recognize a very similar mindset of high-tech innovation for renewable energy systems in Israel, and also in Israeli knowledge institutions. And we foster our long-standing collaborations with them. For example, we collaborate with the Technion in the Eurotech Alliance, or we collaborate closely with the Ben Gurion University on solar cell research. And I think that now, especially that we have seen that in the last year with COVID and political instabilities that resulted in closing borders and a more inward focus of our countries, that it is very good that we have this Israeli-Dutch Innovation Center to connect bright minds and innovative companies across our borders. For in the end, I think the energy transition is a worldwide challenge that cannot be solved in isolation. And therefore, I'm really looking forward to the presentations of today, and I hope that they will lead to many useful collaborations in the days after. Thank you.
Thank you very much, Mark, and thanks again for co-organizing this event. I'd like to introduce our first speaker, Professor Richard van de Sanden, who is the scientific director of the Eindhoven Institute for Renewable Energy Systems, which was just introduced by Mark. He's also a group leader of plasma solar fueled devices at the Dutch Institute for Fundamental Energy Research, DIFR, and a full professor at the Department of Applied Physics at the Eindhoven University of Technology. His work specializes in applying new advanced diagnostics for gas phase species detection, as well as in situ analysis and control of the physical and chemical properties of the materials processed. He has authored and co-authored over 550 papers in peer-reviewed journals and is the co-inventor of over 20 patents. Richard, the floor is yours.
You need to unmute, Richard.
Okay. Thank you, Racheli, for this very kind introduction. I'm also very glad that I can be present at this exciting workshop to give a little bit more depth on. I have to switch now, so that it should be okay.
Now it's great.
Yes. Okay. So a little bit more depth on the realization, I think, within the Netherlands that the production of, let's say, green hydrogen and green chemistry requires also a massive deployment of, let's say, the high-tech industry. And I think Eindhoven, in that sense, is one of the regions where this is, let's say, on the DNA of all the employees here in the region, but also, of course, of all the innovation institutes and the Eindhoven University. And that's what I want to bring to the floor. And I will give a little bit more depth that, let's say, deploying an industry, or let's say working on the energy transition to get sufficient green hydrogen and green chemistry for the decarbonization in the end also, is that you need to actually realize a totally new industry. And that's actually where IRES is going to be positioned. So this is of course known, and I just want to stress on this slide that we have to realize, and I don't know whether everybody at the moment really deeply realizes this, but the next 20 to 30 years, there's going to be a fundamental shift in the way energy is generated, stored, delivered, but also valued and purchased. And that's basically also giving the deep complexity of this energy transition. It's not only on the technological side, but it's of course also on the societal and the social economic side. The driver for that are, of course, all these agreements which you make, and what we are present in is basically, if you look at this picture, which is from the European Union, and I think it very clearly indicates what transitions we have to make. We see on the left side in this picture, we see how actually the energy system is of today. It's basically linear, very much centralized. We have central power stations, central production of our fuels, etc., in which also a lot of waste is introduced. And we have to go towards that picture on the right, where centralized power generation is going to play still a role, but also decentralized power stations are going to role. Prosumer-consumer interactions. All these aspects come back in this, let's say, future, and in this case, it's mentioned the EU integrated system, but you could actually read here the global integrated energy system. And so we need to go to more efficient and a more circular system, because apart from the energy transition, we have also two other big challenges, which is the material challenge and, of course, the feedstock challenge. The feedstock challenge, more and more. We need to go to cleaner power systems. Basically, we are deploying this at the moment, but also to a cleaner fuel system. And then, of course, the biggest hurdle here is that this is all going to be based dominantly, probably, on renewable energy systems. As you can see here, on the one hand, wind and sun, they have, of course, as the biggest disadvantage that supply and demand is a mismatch in both time and place. And that's something we need to solve, and that's why transport, conversion, and storage of renewable energy is going to be key. We need to massively accelerate. I showed you the carbon budget we still have. We need to accelerate. And of course, we have a lot of knowledge on how technologies develop once you start scaling them up. The so-called learning curves are very important there. And here you can see for some of the important, let's say, storage and conversion technologies, you see some of these learning curves. You also see two of older storage systems, pump hydrogen and the lead acid battery. As you can see, there's almost no cost development there because it's a mature technology. But you see that there is a sharp decrease in cost per unit of in this case, kilowatt hour stored, while scaling it up. It should be realized that this is not just linear scaling up, but there's a lot of innovation still necessary to get these learning curves. If you do not innovate, if you do not improve manufacturing technology, if you do not improve, let's say, on better materials, more efficient materials, robotization, and that kind of stuff, you will not get these type of learning curves. They are really a result of an R&D and innovation-driven deployment of scale. And you can see this, for instance, very clearly in solar. You see almost an exponential development of let's say, the solar energy deployment at the moment. And maybe good to mention that EIR has never predicted this. They always were much conservative. So
recording in progress.
And it is possible if you indeed take into account let's say the rules of innovation and R&D. So that's basically where we positioned IRES. That's our vision. We want to actually exploit now the fact that these learning curves, they have actually to do with the numbers you actually produce. Think about the T-Fort, but also think about this example of solar. Solar is basically a modular technology, and you have much smaller scale sizes of let's say, deployment. This in contrast to what we have so far in this linear energy infrastructure, where everything is central and large. Probably the future, and that's actually where we aim for, is in the granularity and finding actually this size with which we have to scale is actually key to actually get a further cost reduction, and with that an acceleration of the energy transition. And think about the size of solar is now more or less established. We have panels which are under 300 to 400 watts. For wind, we also know we go to probably 5 to 10 megawatt. But this will be, let's say, the size with which we are going to scale. What is the size for electrolysis? Is this gigawatt scale, or is this on the 100 kilowatt scale? I think that question is still out, and it's very interesting to know whether that what the size will be. There are all kinds of benefits. If you here you can see the unit cost or unit size. They are basically strongly correlated, but you can see that there's a lot about introducing a technology if you have smaller scale. If you have a smaller size unit, these delta T with which you actually introduce the technology is much faster. On the other hand, also the conventional learning rate is actually much higher. So the depreciation in cost is much higher for smaller scales. And this, of course, all has to do with assets, but also with, let's say, that learning curve, which is much steeper if you have smaller size units. Okay, so this is already more or less been introduced by also Robert Jan and Mark. So that's what we have actually established here, and it was launched last year, the Eindhoven Institute for Renewable Energy, with the vision of working on, let's say, renewable energy-driven systems from a perspective that, scaling by the numbers rather than by the size. And of course, for every technology, there might be a different perfect size to scale. And we want to do this in close collaboration with the high-tech manufacturing industry. And to give you a little bit more depth on what that entails, let's have a look for the Netherlands. And I think the Netherlands has, of course, a strong gas infrastructure. And that's because we had a very big field of gas here. But it's going to be closed down. We have, due to this, also a lot of chemical clusters, but also because we are a port of Europe, we have, of course, the backland. Think about Belgium and Germany, which are basically, the Netherlands is the harbor for that, to get a lot of transport. So there's a lot of chemical conversion, chemical technology, big, large chemical plants. Now, if you go towards this new future, you have to think about how to scale this. And is this really going to be centralized as we have seen now? Or are we going towards this modular scaling? And I think that's where we want to position ourselves. And we want to connect this Brainport high-tech region in which there is Eindhoven, but there's another very strong cluster on electrochemical conversion in the region of Overijssel and Gelderland, let's say surrounding the old company of AkzoNobel. And we want to make this clear connection to actually drive this energy transition. And for that, for instance, it takes a lot of effort because the high-tech manufacturing industry in the Netherlands is not yet well aware of, let's say, these large opportunities which are there. And that's why we actually, as IDIC, teamed up with VDL, which is a big high-tech company in the region, to start work on what we have called the Dutch electrolyzer. And it's basically looking at the manufacturing of a Dutch electrolyzer to get costs down. If you make a deeper analysis, and now this is actually a scheme which came out of a working group to actually visualize what is needed to actually get cost reduction within electrolyzer production. And maybe also we are doing this exercise to, in the end, also look at, let's say, the green chemistry, because that will probably have a similar way of system architecture. And if you look at this, then basically this high-tech industry can be involved on many positions within the value chain. On the production side, looking at, for instance, high volume manufacturing of all kinds of electrodes or bipolar plates or membrane assemblies, conversion stacks, how to actually integrate this in a clever way and how to make sure that the high volume production is actually really giving cost benefits. Power and control, because you have to eventually make an electrolyzer of a certain scale. You have to connect power and control, sensoring, etc., etc. Then this system has to be included in a much larger power system. How do you distribute the power from wind towards these electrolyzers? But there's also the question if it comes from solar, and how do you do this in a bidirectional grid where you have productions within the maybe built environment and bring it to regions where you do the power conversion to hydrogen, for instance. And then transport, storage, distribution, etc. Probably you need buffering of, let's say, hydrogen in large caverns. And that's what we're also looking at. And again, for that, you need pumps, compressors, etc. So we need to work on this full value chain. And you can see that this is actually a totally new industry we need to deploy. And this actually lines up with an advisory from a report of the ECCM committee, which is involved in advising, let's say, the top sectors in the Netherlands on electrochemical conversion and materials. And here you can see, to reach the goals, we need to have strong R&D within, let's say, the hydrogen production, but eventually also to look through after 2030 for the, let's say, green chemistry, where we more and more are going to look towards direct chemistry. And this is, of course, interconnected by building up this manufacturing industry and, of course, training and educating, let's say, the human capital of the future. Now, this actually all comes together also very nicely in a recently, more or less prohibitively granted growth fund proposal, where I want to stress that this is basically an R&D proposal of unknown and massive, let's say, funding. It's about 238 It's unknown in the Netherlands, 238 million euros for the R&D component and about 100 million for a small-scale hydrogen project. And basically, you could say, if you know a little bit Dutch, it's about scaling up and innovation. Oh, sorry. About scaling up and innovation, building up and rebuilding, and educating, and let's say redirecting the jobs for the future. And it's essential to keep these jobs in the large, let's say, chemical industries we have in the Netherlands, and let's say everything in connection to the gas industry, but moreover to create these jobs in building up a high-tech manufacturing industry for green high-tech technology. And with that, I want to thank you for your attention, and I'm open for any questions you might have.
Thank you very much, Richard. With your permission, we will have the questions at the end of our session.
Okay.
Thanks. My background is in the initiation and management of EU projects, and I was actually trained by the Commission. And one of the keywords at the Commission at the time in Brussels when we were evaluating proposals was multidisciplinarity. It was extremely important. And what I can see from what Richard described is that there is indeed a need for multidisciplinarity and also for internationalization. There was another very important parameter when we were evaluating EU projects. And this is what we here try to implement in these Dutch-Israeli mini-symposia. And therefore, I'm now going to introduce a speaker who is coming from a field which is a little bit adjacent. He is not operating yet in the field of hydrogen, but I think that his expertise and also that of the next speakers is extremely relevant to building up this capacity, the human capital capacity and the technology for the production of green hydrogen. With these words, I'd like to introduce Professor Slava Freger, who is a PhD summa cum laude from Ben Gurion University in the field of chemical engineering. His expertise is membrane technology, desalination and water purification, physical modeling and advanced characterization of membranes. Among others, he is also working on deposition and biofouling fuel cell membranes. Slava, I would like to invite you to give your presentation and to show us how your expertise fits into this larger picture of the development and the production of green hydrogen.
Thank you, Racheli. Just a moment. I'm struggling with sharing the presentation, so just a moment.
Take your time.
Okay. Okay, so it's just it was at the end because of the test. It was at the end of the presentation, so just a moment. I will just get it back. Okay, now it should be fine. Yeah. Okay. So do you see it?
Presentation mode.
Right click on the screen.
So do you see it well now?
Okay, let's continue like this. It's okay. You can leave it like this.
Actually, I do see it. Just a moment. I am probably it's just about switching between the screens.
The computer needs to be on duplicate and turn off the presenter view.
No, it's not about the presenter. The presenter view is off at the moment. It's just about the screens, I think. But I never had it before, so I'm trying to figure it out.
You have on the bottom right, you have the play button.
an icon on the screen.
Just looking for the screen that I have to switch.
Bottom right, please.
I suggested you will do it the way it is now. Okay, just start from the beginning and we'll handle it the way it is. You can go back to your first slide now.
Okay, so I will just try to do that.
That's okay.
Apologies for that. I usually know how to solve it, but in this case, I don't see the place where I do the switch. Okay, anyway, so sorry about that, and I'm really pleased and delighted to be part of this event. A very impressive first presentation. It gives a very, very broad vision for the future. So I will try to take you to a very different, to have a look from a very different angle. So first of all, I'm coming from the field of desalination, and I'm actually, I have to admit, I don't know many faces that I see here. So it's a great opportunity for me to get familiar with this community. But I also have an interest in energy production and electrochemical technologies for energy, for hydrogen, for mobility, and that's why you can see in my background the logo of Grand Technion Energy Program. So this is one body that you can see myself as a representative of this, and I will be more than happy to be a link between this group and this energy program of the Technion. Energy program has been also involved in a very big Israeli-based consortium, which is called INREP. This is a center, National Center for Mobility, Electrochemical Mobility, or Electrochemical Propulsion, which actually unites today virtually everyone in Israel engaged in electrochemistry. So I will mention that at the end as well. So I will be more than happy to be a link to that community as well. I think it is highly relevant to what was talked about during the first presentation. And so now I will you can see that the title is a little bit different. So that was probably let's say my initiative to change the title a little bit, again to just stress the point that I'm mainly engaged in desalination and not as much in hydrogen energy economy, but as I said, we do have a connection, and so the connection in my case is you can see it through this particular let's say title, energy, water energy nexus. Some people add to this food as well, but let's focus on water energy nexus. And so we can see that these problems of water and energy are global problems, and they are very closely interconnected. We feel it particularly well in Israel because desalination today is a very big part of our water consumption and water market in general. We surely will hear about that in the next talks. And energy production is very heavily dependent on availability of clean water. And on the other hand, water production, especially in Israel, when we use a lot of desalination, is a very heavy consumer of energy. And so today it's a very significant part of our national energy consumption. And so any means that allow us to reduce this consumption is very beneficial for everyone in Israel. And I think the same trend will spread to many other countries, especially in the Middle East and countries like India, south of Europe, the United States, and so on. Okay, so So when we talk about water, energy, and access, so you saw the diagram before, how the flows of water and energy are closely connected, but there is another link between the two things. And I want to focus on that because this is basically the area of my expertise. And this is membrane technology. Membrane technology supplies the solution to both of them, at least partial solution, or it is a part of those systems. So of course, membrane technology enables what we have today, a wide, large scale desalination. It also covers water purification, which is a kind of a smaller market today, but also very important and probably is going to engage more in the membrane technology and use more membranes in the future. You can see here a desalination plant, one of the plants in Israel. You can also see the technology, a slightly different technology. This is ultrafiltration technology or membrane bioreactor technology that is used to purify water. But this is only a small part, and it's going to expand to other membrane technologies in the future. On the other hand, when you talk about energy production or electrochemical mobility, we also use a lot of membranes. So membrane is also another very important separator that separates fuel and ion flows inside the fuel cell, and that allows a high efficiency. But in both technologies, we still need a lot to do and improve, especially in electromobility and energy generation using technologies like fuel cells, as well as conversion of energy and storage of energy, for instance, using electrolyzers, as we heard in the first talk. And so when we talk about membranes, so membranes offer lots of different selectivities, and quite a few of them can be used in what I mentioned before, in water desalination, water purification, for instance, using electro-dialysis, or fuel cells, as well as electrolyzers, which is not mentioned here. But this is basically a reversal of a fuel cell in many senses. So I tried to put here just the key points of what we need to do with the membranes for two fields. So in water purification, basically we're in a very good position because the current membranes are performing very well for desalination. But still there are a few points that you can see here. For instance, the polyamides are not perfectly stable chemically, and so for instance, we would like to improve greatly the stability to chlorine. They cannot reject certain pollutants, and they don't have a very good selectivity between the ions. And so this is one of the points that are becoming very important, for instance, in the context of resource recovery, where we really can reduce or utilize energy in a more optimal way for actually generating valuable products from the waste. And if we talk about fuel cells, so there we have this benchmark membrane called Nafion. So its structure is shown here. Probably all of you know about this. But Nafion is not perfect as well. And here the problems are even more severe. So we would like to improve greatly the resistance, or to reduce resistance of Nafion membranes. We would like to improve temperature stability. As you can see here, the performance of Nafion membranes decline at high temperature, where exactly we want to be in most cases, because in those cases, we can utilize catalysts, very expensive catalysts, in the best way. It also has a high crossover of fuels like methanol, which are considered to be alternative to hydrogen in some situations because of higher volume energy density and other attractive things. And so I will just show you a short glimpse of research to the research that we are doing in both directions. So one example that I want to show is actually use of desalination, not in the large-scale seawater format that is used today, but for using it to desalinate wastewater. And so the first two stages of wastewater treatment, municipal wastewater treatment and partially industrial water treatment, is shown here. Tertiary water treatment is actually very rare today. It is used only in very few locations over the world, in Europe mostly. it costs a lot, and there is a debate if it's necessary, but in Israel especially, and probably it's going to be valid for many other countries in our region, is that salinity of wastewater is going up. So the most efficient use of wastewater, recycled wastewater for irrigation, is becoming a problem. And here you can see the chloride level in Israeli water, including water sources such as Tiberian Sea, are rising and approaching 300 level, which is kind of critical for agriculture because you cannot use it for plants. By the way, humans can consume this water easily. So for humans, the limit is much higher, but for irrigation, which is, as I said, the most efficient use of tertiary water, is not good. So the problem is when you try to do it in an energy efficient way, for instance, using nanofiltration, which is not as selective, but allows to remove enough chloride and so upgrade the water for irrigation, we have a problem of phosphates, calcium phosphate scaling. And this is quite unique for municipal wastewater. It does not exist in seawater desalination. And so you cannot recover much water because your membrane starts getting clogged very quickly. And so when we looked into this problem, we realized that the actual problem is very high rejection of ions such as sulfate, which is kind of a twin brother of phosphate, a good model of phosphate. And so here you can see that sulfate and phosphate are rejected in a mixture very well, similarly well. And as a result of very high rejection of phosphate, you have a very severe precipitation of phosphate on the membrane, which clogs the membrane much earlier than you can see actual precipitation in the solution. And so what is the good solution to that? The solution is actually to reduce rejection of these ions, all these ions, divalent ions relative to sodium chloride. But unfortunately, the physics of desalination works in the opposite way. And so we had to figure out what to do about that. And so we realized that if we use polyelectrolyte membranes, we can actually play with the mechanism and utilize a mechanism which is different from what is used for seawater desalination membranes. In particular, we can use Donan exclusion, the same one that is used for ion exchange membranes used in fuel cells and electrolyzers. And in that way, we can reduce the rejection of phosphate and sulfate very, very strongly. And as a result, you can see that when you have a more flat pattern of rejection of different ions, the scaling, which you can see reduces severely the flux of water by commercial membranes due to scaling when it reaches something like 50% recovery. With our membranes, you can keep going and recover 90% without seeing any problem with scaling, and yet having enough rejection of salt, which is the most important thing. Another important thing is that actually you keep in water ions, something like phosphate or calcium or magnesium, which are very, very beneficial for irrigation. And so this is just one glimpse. In this way, when you don't require high rejection of ions and you have like kind of flat pattern, you also save a lot of energy because you don't have to overcome so much osmotic pressure as well. So there are multiple benefits here, and this is probably a good example of tailoring membranes for a particular application, which is very important and energy consuming as well. Another thing is, so we looked into what we can do based on our knowledge in membranes in systems like fuel cells or electrolyzers, where naphthalene is the main and most important benchmark membrane today, and there is no alternative in sight actually. And so our question was whether we can improve that. And again, we looked into the physics of conductivity, and we know that that naphthalene has a very unique structure composed of elongated nanochannels, which are conductive channels. And due to these elongated channels, it has very unique conductivity, much higher than other alternative materials, especially when it comes to lower humidity. And people realized quite some time ago that when you align those channels in this way, for instance, you can improve conductivity in certain directions. So there is a lot of potential of utilizing Nafion features in a much better way than in just native Nafion. You can try to, for instance, mechanically extend or draw Nafion, and that improves the conductivity. You can also try to take it to extreme and use something which is called electrospinning to actually induce very strong alignment within fibers. But the question was, you can see here that for very narrow fibers, you have a very high conductivity, an order of magnitude high conductivity. And you can also see in this way the channel alignment. The question is how you can make it through the membrane, not along the membrane, not in plane, but through plane. And that was actually an idea that we want to use. So we electrospun Nafion with another material, PVDF, which stabilizes Nafion structure and improves this thermal stability. And then we applied this very simple approach to actually create buckling of those fibers. So the native configuration of fibers is in plane, so in this direction. But once you compress this Nafion membranes in this way, you can actually induce alignment of fibers. And if you remember, channels are aligned within fibers. So we combine here macroscopic and microscopic alignment to create a very high conductivity through the membrane. And you can see here that we can see this alignment of fibers using TEM, so down to very low resolutions. We also see the stabilizing effect of PVDF on the Nafion structure, which helps to keep this alignment sustainable. And we also see the effect of conductivity. So we can see that the through plane alignment is increasing, and the in-plane alignment is decreasing, which is an indication of through plane alignment of fibers. And in this way, we can actually have a conductivity which is higher than the original Nafion conductivity, despite the fact that Nafion is actually only a fraction of this membrane, about 50%. So at the moment, we are trying to improve that in order to get a membrane that we can be tested and utilized in fuel cells or electrolyzers. And so at this point, I will just conclude. So I will thank my group, of course, who did all this work that I presented and many other things. And I would like to draw to your attention to this consortium, which is again called INREP. This is Israeli National Center for Electrochemical Propulsion, which actually roof organization today for all electrochemical research in Israel. It is focused on fuel cells and batteries. It is led by people from Bar-Ilan University, particularly Professor Doron Orbach. And so I will be more than happy to be linked to this community, which is going to actually last for quite a few more years. And it includes a lot of people engaged in fuel cell research, energy storage, hydrogen generation, and so on. So at this point, I just want to thank you for your attention, and I'm open to questions. Thank you.
Thank you very much, Slava. And we will have the discussion at the end of our presentations. I'd like to introduce now Pepijn Flux, who is the Business Development VP at Redstack BV, the Dutch company. And Pepijn has 25 years of professional experience within both corporate, SME, and startup organizations. He joined Redstack after resigning from a key position in the energy transition domain at the largest Dutch regional grid operator. He holds a master's degree in mechanical engineering from the Technical University of Delft, and he will tell us about the electrodialysis for water desalination. Pepijn, the floor is yours.
Yeah, thank you so much, Racheli, for having the opportunity to present our company, Redstack, and also Many thanks to the previous speakers for their inspiring and relevant presentations. The title of my presentation is Electro-Dialysis for Water Desalination, but in fact it's also about the water energy nexus. First, a short history about our company. We started in 2005 as a spin-off of WETSUS, the European Center of Excellence in Sustainable Water Technology. In 2014, we built the first operating blue energy pilot plant. And in 2016, we received the Dutch National Icon Award for being a Dutch impact scale company. Since that moment, we participated in about 20 national and international R&D projects, and we have filed and acquired 15 patents. The core of our know-how is in the electrodialysis process design, membrane application, and stack performance. Our founder is still a single shareholder, and he's deeply involved in the company since the foundation. And we have a great team of experienced professionals, both in the water industry and the renewable energy industry. And we have partnerships with some relevant organizations. The mission of RedStack is to turn our technology leadership into global market leadership of process technology and ion exchange membrane stacks. RedStack is part of a group of companies. Our sister company, Pure Water Group, focuses on design, manufacturing, and sales of professional skid-mounted process units and engineered solutions for ultra-pure water production. They use EDI modules and also ED membrane stacks from RedStack. So we have a great synergy over here. Also, we have a relationship with the company Aqua Battery. Aqua Battery is very interesting because they have developed a 100% sustainable electrical storage system, which is solely using water and table salt, and they're using the membrane stacks based on ED and RD technology. And RedStack will be the sole supplier for Aqua Battery. Then something about our technology. It's deployed in two market segments, in renewable energy generation and water desalination. First of all, about RED. RED is the process where fresh and salt water are combined. The charged ions, they flow through our selective membranes. These are placed in a stack, and then a voltage difference is created between the electrodes. In ED, electro-dialysis, the driving force is the electrical potential. So salt water flows between the selective membranes. Membranes are placed in the stack, and an electrical potential is then applied between the electrodes. So the result is a concentrate of salt water and a product of desalinated water. RedStack has designed one generic tube stack, which is applied for both our RED and ED configurations. Then about blue energy, or also called salinity gradient energy. This technology to harvest this energy is relatively new and innovative. So much research needed to be done to investigate the potential of this new source of renewable energy. Several renowned organizations have been working together on this exercise to indicate locations where seawater meets river water, but also where seawater meets brine water, for instance. They plotted this map, and they concluded that the theoretical potential of salinity gradient energy that is available across the globe is about 1 terawatt. This does not mean, however, that in all these cases blue energy can be harvested. So consequently, research has been done on local situations, on water conditions, on required infrastructure and level of technology, etc. So we conclude that the practically extractable amount of blue energy could achieve a share up to 12% of the current global energy mix. So in our opinion, that is a very attractive potential. Blue energy also has several interesting characteristics because it produces continuous power as long as salt water and fresh water is available. Wind and solar energy have intermittent characteristics, and therefore they have a relatively low load factor or capacity factor. Blue energy, therefore, offers a capacity factor which is close to 100%. So this adds more stability to the electricity grid with zero carbon emissions, and also, very important, a minimum impact on landscape and ecology. This is an overview of our current pilot plant in the north of the Netherlands. On the left-hand side, you see the Waddenzee, which is part of the North Sea. In the middle, the blue box is our operational pilot plant for blue energy. And on the right-hand side, you see the IJsselmeer, which is the largest freshwater lake in the Netherlands. In the middle right, you see freshwater, which will pumped into the plant. And on the left side, seawater will be pumped in and brackish water will be pumped out. The location is the Afsluitdijk in the north of the Netherlands, which actually is a dam of about 32 kilometers, and it forms a crucial part of the Dutch water management infrastructure, and therefore Redstack has to comply with many strict environmental and safety regulations. And these pictures give you an overview of our current pilot plant. So top left, you see the sand water filtrations on the outside, and the top right, at the inside of our facility, at the left-hand side, there's an array of RED stacks, and on the right side, you see an array of our desalination stacks. We have demonstrated the desalination of water with our ED stacks in the Horizon 2020 project Revived. This was a research project with a budget of almost 10 million euros and 10 consortium partners, and it has been completed after 15 months. We have applied their ED in 3 desalination configurations. First of all, brackish water desalination systems, which were powered by PV, that were located in 3 countries in Africa. We had an integration RED and RO system for low energy seawater desalination, which was built in Spain. And we have set up a multi-stage ED system for seawater desalination. This configuration was built in our pilot plant in the Netherlands. You can find a lot of background information and videos and all publications of this project on the website of Revived. So, if you take a look at the market for desalination and the installed capacity, we see that in nearly 70% of all the cases, RO is the applied desalination technology. ED, the ED share is still relatively low, about 3%. So this relates to about 3 million cubes per day. But we also see that there's an increasing interest in electrodialysis due to the growing environmental restrictions. ED has several advantages because it reduces carbon emissions as ED has a low energy consumption, it's low, several kilowatts per hour per cube. ED offers also very flexibility in the level of desalination that is required in product water. It contributes to increased water recovery. And very important as well is that ED increase the recycling of chemicals because nutrients and chemicals are maintained in the process, so these can be recycled, and the additives of new chemicals is well reduced in this sense. But due to our track record, we have been working on hybrid system configurations as well that can reduce the energy consumption, also the water recovery even further. So if you take a look at the first example on the left, it's an industrial process with seawater and also treated wastewater, where, for instance, RO and ED is applied. And then RED can be implemented using the concentrate of the RO or the ED, and also the treated wastewater as the feed waters. This generates renewable energy, but it also decreases the salinity level of the discharge. The second example, it's a more advanced example on the right side, which is also an industrial process with seawater with an RO installation. Then ED can be implemented using the RO reject to desalinate the reject to seawater level and feeding the product back into the RO feed. This reduces the feed water usage to get a similar product volume, or it increases the recovery when the RO is adapted to this increased feed flow. But moreover, the concentrate of the ED, which has a higher concentration than in the first example, it can be used in combination with treated wastewater, is flowed to feed RED stacks and then to generate renewable energy, and then also to decrease the salinity level of the discharge. And then to conclude my presentation, making a bridge to clean hydrogen production, Redstack is also able to contribute to this process. Well, first of all, obviously, we would recommend that in any situation or any location where salt and fresh waters meet, to generate renewable energy or blue energy by using RED immediately and locally. But when electrolyzers are installed, because there's a demand for clean hydrogen production, then RedStack enables this process in two ways. First of all, by providing continuous renewable energy with our RED membrane stacks. And second of all, by our ED membrane stacks that can be part of the complete purification process to provide the proper feed water for the electrolyzers. And in such a configuration, our sister company, Pure Water Group, would provide both the ED and EDI installations. And that's what I would like to share with you.
Thank you so much, Pepijn. We definitely learned a lot. And I would like to now introduce our fourth speaker, Tomer Efrat, Director Business Development at the Israeli Desalination Enterprise Water Technologies. Before I do that, I also feel that I should tell you that at the embassy, we have a second officer for water and climate, my colleague Jasper van Maastricht. And as some of the activities that we are discussing today are related to water, and you can then, of course, also approach Jasper in order to develop further collaboration in that domain. Tomer is the Director of Business Development and Product Management at IDIC Technologies. He has an extensive background in the fields of SWRO, brackish water desalination, thermal, and IWT. He brings over 13 years of comprehensive knowledge in technology management, business development, process engineering, and R&D. He holds a bachelor in mechanical engineering and an executive MBA in business management from Tel Aviv University. And Tomer will tell us about desalination technology in the use of electrolyzers.
Thank you very much for the introduction. I'll just share my presentation. Do you see it? Do you see it okay? Is it fine?
If you can put it in
It's
presentation.
not. Okay. Is it okay now?
Not yet.
And then cancel presenter view.
Sorry?
Right click and then
Cancel presenter view.
Better now?
not yet.
I think you need to click display settings on top and then switch.
This is exactly what I did. This is exactly what we did in the rehearsal. Maybe I'll just plug out the secondary screen that I have. Not yet?
No,
Try it again.
If you switch the PC to duplicate, it would be okay. So
Is it okay now?
the screen.
Instead of you, would that help?
No, maybe now.
We don't see your presentation yet.
Oh, maybe I'll just share it again. Sorry for that.
It's okay, no problem.
I must say that I don't actually see the screen anymore. Sorry
Okay.
for that.
Okay, now we see you start screening. Great.
I don't see the.
Now it's perfect. Ah, sorry. This is Leo. So let's start. You have now Leo who's going to screen your presentation. Tomel?
Can you see me?
Yes, we see you. Would it help you if Leo will now screen your presentation?
Do you see it now?
Yes,
Yeah,
now we
yeah.
see it. That's fantastic. Just
And
put it on.
are we fine or in presenter mode?
It's okay. Let's see it as it is.
Okay, thank you. Sorry for the technicalities. Okay, so I'll start. So after I stole some of the time. First of all, a few words about the IDE. IDE was established in 1965. We're considered as a technological leaders in desalination and water treatment, both on membranes and thermal technologies. We have hundreds of installation over 40 countries worldwide, and we have offices. Our headquarters is here in Israel, but also offices in the US, China, India, Chile, and Australia. Today, after we saw some presentations about in-depth on the membrane technology and some of the electrodialysis, I'm going to focus on the, I would say, more common technologies and look at it at a bit higher level and not directly into the tube or into the membrane itself. Basically, when we're going to when we're interested to desalinate seawater, we have two groups of technologies, the SWRO and the thermal technologies. And I will focus on that. I would like to say that when we see some opportunities in the green energy, we see more and more projects that are trying to utilize wastewater as feedstock for the desalination and further into the green hydrogen. But I'm going to focus here on the seawater DSL. This is a typical RO process. I would just like to mention some important aspects in it. After we saw some presentations about the membrane themselves, it's important to say that we see great importance in the entire process, mainly on the pretreatment part of the desalination plants. In many cases, you will find use of either gravitational filters, GMFs, or UF for that matter. And this typically comes after some raw filtration. Some companies uses chlorine or ozone in order to clean the water and before it goes into the filtration stage. In IDE, I would say that we typically do not do that in order not to promote biofouling growth on the membrane. After the filtration stage, as you all know, we're going into the RO membranes. It can be either one stage or two stage, especially if we're looking at generating ultra pure water. We will typically go with two stage in order to get to very high quality water before we go into the polishing stage that can either be ED, the red that we just saw, CDI, or in some cases even chemical treatment by using mixed beds. This allows us to significantly reduce the TDS levels in the permeate of the RO plant below the level that is required for electrolyzers. One example, just a few pictures of current plant. This is a picture from the Hadera plant. This is a better view of the plant. Last year, this plant generated 150 million cubic meters of water for the state of Israel. Very good plant. I can show you just from above how does the treatment stage, how do the treatment stages look like in this plant. We start by the pre-treatment, followed by the SWRO, the main filtration and main desalination stage. The second stage is actually cascade of 3 to 4 stages where we polish the water, remove excessive chlorine and chlorides and boron from the water. And in case of seawater desal for municipal use, we also need to reharden the water using pre-treatment, and then the water is delivered to the product water tank, and from here to the water utility of Israel to Mekorot. I guess this has become the mainstream technology for seawater desalination. In most cases, some people say it has become a commodity, SWRO, but I would like to share some maybe a bit more, I would say, older technologies that can definitely be utilized into in order to generate high quality water for the electrolyzers, and especially if it's a part of entire system. And then when I'm relating to other technologies, I would like to refer to thermal technologies. Those can be either MVC, mechanical vapor compression, or MED. MED, multi-effect distillation. The MVC is operated by electricity, and the MED by steam, or actually waste heat. And I would like to show a very short clip about the how the MVC works. So I would share. I hope this sharing will be easier than the previous ones. 1 second. Sorry for taking a bit longer. Okay. this will go a bit smoother than before. Do you see the presentation okay?
Yes, we do.
Okay, great. So the MVC that I just presented, it's actually generating distillate. It's very high quality, about 1 ppm TDS. And the main advantage of this technology, especially when we're talking about electrolyzers, is the fact that it is very robust. I would say the most robust technology for seawater desal. It's fully automatic, and it can tolerate fluctuation in seawater quality. We don't need to treat the water so much like we do with RO. We can tolerate TDS levels of 10 or even 15 with some level of organics and oil, and the unit will just take it. And for clients who are considered as mission critical facilities like power plants or data centers, they typically are looking for this type of technologies. As I said before, we installed hundreds of them. And this is a very robust solution for seawater desal when the capacity is not significant. And when I'm saying not significant, we can reach up to about 3,000 cubic meter per day with a single unit with a 3-stage. You can see here small unit with 1 stage, about 500 cubic meter per day, 2 stages between 1,000 and 2,000, and the 3,000, even a little bit higher, is achieved by a 3-stage MVC. The MED unit is similar in terms of the evaporator design, but it is not operated with electrical compressor. It is operated by using waste heat. And this is suitable where the entire operation includes also steam generation, where some of it can be diverted into seawater desalination. The permeate quality, the product quality will be similar to the MVC, about 1 ppm TDS. And we can reach very high quality, as I said. This unit is operated at configurations that start from, let's say, three evaporators and can go up to 14 evaporators or 15 evaporators in order to enhance capacity and desalination efficiency. The larger units can generate up to 25,000 cubic meter per day. The units that you see on the upper left side is the largest desalination plant in China, which consists 8 of those units with total capacity of 200,000 cubic meter per day. And of course, there are many others. The main benefit, as I said, is the ability to use waste heat with actually very low graded heat in terms of pressure and temperature that can be supplied from a variety of industrial applications. It can be waste heat from refining process, extraction steam from steam turbine, back pressure from the steam turbine, and even hot water from any process that utilize cooling water and generate hot water that actually displays the heat into the environment. Just a small example. This is a configuration where the MED is connected to a steam turbine, but of course the steam can come from any process. One of the main issues that is raised when we discuss seawater desalination is what are we going to do with the brine? And there are many solutions for that. We all know that, especially when we're talking about green hydrogen, it's also important that the desalination plant that is supporting this process will also meet the sustainable levels that are required by the entire process of green hydrogen generation. the typical solution that we are doing, that we are implementing in order to avoid any effect on the environment is, first of all, if we're adjacent to a power plant or other industrial facilities that uses cooling water, the best solution is by dilution. We're just mixing the brine with the cooling water. What you can see here on the right-hand side is the outfall water that comes out of a power plant, which is adjacent to the Hadera desalination plant, and we are just mixing the brine of the plant with the power plant cooling water, and by that achieving very good quality of brine that is living into the sea and causing no harm. And in case that this solution is not available, we are typically using brine diffusers that spread the brine in such way that it won't be concentrated in a single location and will cause bad effects on the marine environment. And of course, we can move forward and think of other solutions. Those will require further treatment, but it also provides some benefits. Those additional treatment will, of course, increase the cost of the desalination. But when we're looking at a combined operation where the electrolyzers and the green hydrogen operation itself is much more energy intensive and cost effective. Addition of some elements to the desalination plant may be optional, and as I said, may generate more products from the desalination process. One example is the same desalination plant in China. What you can see behind it is not the sea. Those are evaporation ponds. When the brine of the desalination plant is being used in order to generate salt, sodium chloride, they are precipitating in the evaporation ponds, and the salt is being used by others. Of course, we can take the process much further. This is a configuration that we designed for green hydrogen operation, which we're interested in a full ZLD solution, meaning there is no brine discharge back to the sea, and we're able to also generate some byproducts from this process. As you can see, we're starting with the straightforward RO process with a clarifier, gravity filter, UF, and then the RO plant. We have 3 stages of pre-treatment because the water, I would say, is a bit nasty and calls for extensive treatment. But the brine from the RO plant is not rejected back to the sea, is going through an NF process in order to reduce the level of hardness and sulfate. And then the brine is going into an MED, which increase the TDS levels of the brine very close to the precipitation level of the sodium chloride. And then the brine is being flown into the cooling crystallizer, which crystallizes the sodium sulfate, and then into a thermal crystallizer, which generates sodium chloride. I would say that instead of precipitating those sodium sulfate and sodium chloride, in other application, we are taking this very high salinity water, as I said, close to the saturation level of sodium chloride, and this solution is being used in order to generate chlorine in a chlorine plant, which needs a saturated solution of sodium chloride. So there are ways to utilize the brine and not just dispose it back to the sea.
Good, if it's okay with you, because we have more presentations.
Yeah, it's actually my last slide.
Thank you.
So, thank you very much.
Thank you so much, Tomil. And I'd like to move on to the penultimate presentation, by Guido D'Alessi, the CEO of Elestor. Guido graduated in physics and started his career in R&D of laser-based measurement equipment. He develops optical disc equipment for which he established a global sales and service network and headed local offices in Singapore and in Los Angeles. In the 8 years that he held a position at this company, the company became global and a technology leader in this field. Guido joined in May 2015 Elestor and is also one of the early investors of this company. Guido, the floor is yours on the HBr flow battery for electricity storage and hydrogen production. You have 15 minutes.
Okay, good morning. That's what it still is, I believe, or good afternoon on your side. Thanks for the introduction. I hope my screen is visible now with the ocean. Can anyone confirm that?
Yeah, we just don't see your...
Okay, you want to see me as well. Okay, no, I can understand that. Okay, so what I would like to introduce is the company Elestor and its technology, originally developed as a pure electricity storage technology. But since we are using hydrogen in this, there's a very nice and unique connection to hydrogen production. So, but let me start with first showing you and introducing to you what this technology is about. So this technology is developed only for large-scale and stationary storage applications, nothing in mobile or maritime or small scale. So obviously in combination with PV parks and wind parks, and we think that eventually these batteries have the potential to be a substitute for peaking power plants. And then, as I already mentioned, there's a connection with hydrogen, which I come to in a few slides. The technology that we use is based on flow battery technology. I already saw in one of the presentations the vanadium redox flow battery mentioned. Actually, there are many types of flow batteries, of which vanadium is one. And the differences between these family members is the chemistry and the chemicals that are used. In our case, hydrogen and bromine. Main reason to choose for these chemicals is that we are looking for the lowest storage cost per megawatt hour, because that eventually determines the business case behind storage and thus the adoption rate and thus the relevance of this technology in the energy transition. Comparing to vanadium, hydrogen bromine is about 20 times cheaper per kilowatt hour. And that helps, of course, if you are looking for the lowest cost storage. A little bit about the technology. Here you see a schematic of how these batteries work. So all these flow batteries follow the same working principle. You see two tanks on the left and on the right, where we have bromine on the left side and hydrogen on the right side. And these tanks are part of a closed circuit, and these circuits meet each other at a membrane, which is very similar to what is used in fuel cell technology. So a proton conductive membrane here. On the right top side, you see the chemical reaction. And for those people who are a bit familiar with this material, the subject, you could recognize that the charging of this battery is in essence an electrolyzer functionality and a discharge fuel cell functionality. So we do that with one membrane instead of separate electrolyzers and fuel cells, and with a much higher efficiency than you would do with standard water electrolysis. The essential difference of this kind of batteries compared to conventional batteries is that power and capacity are not coupled. The power is determined by the membrane surface in the middle. If you double it, you have to double power. And the capacity or energy in megawatt hours is determined by the sizes of the tanks. And this opens up a lot of new applications, especially moving forward when we become more dependent on wind and sun generation, intermittent sources, where you will need to bridge longer periods of time. In other words, need large capacities, but you don't need a larger power. This technology is, if you compare it to, for instance, lithium, is most economic in large capacities, bridging longer periods of time, where lithium ion is stronger, also economically stronger in short duration power. So they basically exist next to each other. Yeah, this is how such a system looks. On the left side, this is one of the systems that we built. So it's a self-contained system in a container. On the right side, you see an artist's impression of a bigger system where the tanks are external, and these membrane stacks, we call them, are in the container. So you can play around. The membrane stacks are a fixed module giving a power of 10 kilowatt, and from there you can modularly build any power that you need, and the tank size that determines the capacity. We'll go very fast through this. So yeah, I already mentioned a few times, cost of storage is our obsession. We did that by choosing the flow battery concept. Within that, that has intrinsically a number of advantages. Within that platform, we have chosen for hydrogen and bromine. The bromine we purchase, well, we actually cooperate closely with ICL, Israeli company, the biggest supplier of this chemical. And then the patent is on how we have developed the membrane stack at the heart of the system. So that's a bit about the battery, but since we are using hydrogen in this battery, we found that there is also a really nice connection. It's called bycatch. It was not the essence of developing this technology, but this technology can form a bridge between, as I always say, the two religions that exist, storing everything in batteries or storing everything in the form of hydrogen. And just going back a bit to the basic, here you see the battery again, the two tanks, the membrane stacks in the middle, connected to the grid, where the renewable electricity is fed in. So this is the standard configuration for which the battery was developed, but we could easily remove this hydrogen tank, and then basically keep the electrolyte tank and the membrane stacks. And then when there is a hydrogen infrastructure, you can use that basically as the storage tank for the battery. This battery produces hydrogen during the charging process and uses the same amount of hydrogen again during the discharge. So and there's a net zero effect on the hydrogen infrastructure, but it reduces the battery, the cost, also the storage costs per megawatt hour, the size of the system, and it also introduces new optimization options. You make a really nice connection between the electricity world and the hydrogen world, and so you have an extra knob to turn here. Yeah, you can take this even further, and looking at this picture, we have done a profound feasibility study with a large corporate for which the name is still under embargo, who operate electrolyzers. Of course, electrolyzers work best at baseload continuously, but they also want to use cheap electricity. So that is a bit choosing between the devil and the deep blue sea, because the electricity is not always cheap, but you also don't want to switch off and on your electrolyzer. And by integrating our technology in this way, we have shown in an in-depth feasibility study that production costs for hydrogen can be tens.
Guido? We don't hear you, Guido. We don't hear Guido, so maybe. Oh. Yeah, so I'm sorry about that. We will move on to our last speaker, who we actually met last week during a VIP visit of the Dutch ambassador, Hans Dokter, at the Sorek Desalination plant, together with my colleague whom I mentioned earlier on, Jasper van Maastricht. So we will hear the talk of Simeon Brober, and Simeon is the CEO of the Sorek Desalination plant. He has extensive experience as CEO at large water technology companies with a turnover of 200 million Israeli shekels, which is about 50 million euros. He has 10 years of experience in water industry, significant experience in dealing with water treatment facilities, construction failures and process issues in various systems. And he is also involved in the design and construction of water treatment plants. Simeon, the floor is yours.
Okay, thank you, Racheli. Thank you also to the speakers and participants. I'll share my screen. Okay, can you see the presentation mode?
Yes, we can.
Okay, so I will give you a short presentation of the Sorek desalination plant in Israel. But let's start with some other figures. Israel's current annual total water consumption is at approximately 2.4 billion cubic meter of water, which is divided into several sectors. 55% of the water goes to agriculture, 34% for domestic use, 5% is for the industry, and 6% to Jordan and the Palestinian Authority. On the other hand, in terms of water sources, 39% comes from natural sources, 24 from treated effluents, 10 from brackish water and brackish water desalination, and 25% from seawater RO desalination. To this date, there are 5 major desalination plants in Israel. In Sorek, Hadera, Ashkelon, Ashdod, and Palmachim, with a total of 600 million cubic meter of water per year, which covers, as I said before, 25% of the total water consumption and 74% of the household requirement, which is an unprecedented figure worldwide. But this was not always the case for Israel. If you compare the water situation in Israel 15 years ago to what it is now, you will see that from a water scarce country that is depleting its natural water reserves, Israel has managed to become a desalination power and an independent supplier of its own water needs. Going forward to Sorek plant, Sorek desalination plant is the largest desalination plant in Israel and one of the largest and most unique in the world. It has a maximum capacity of 24,000 cubic meters per hour, 500,000 cubic meters per day, and 150 million cubic meters per year, but it's is capable of producing up to 180 million cubic meter of water per year. It was constructed, commissioned, and currently operated by means of a BOT agreement, build, operate, and transfer for a period of 25 years. The product water quality requirements are very strict in terms of chloride and boron concentration, up to 20 ppm of chloride and up to 0.3 ppm of boron. For comparison, as you heard before, in our lake Kinneret, Sea of Galilee, which is Israel's main water source, the chloride concentration is around 300 ppm of chloride. So the water requirements are very, very strict. This is also a challenge. The plant is located approximately 2 kilometers from the coast of Palmachim, of course, in the Mediterranean Sea. We have 2 seawater supply lines that go 1.3 kilometers to the sea. You can see them here. And 1 brine discharge line that goes 2 kilometers to the sea. On each of the supply lines, there is an intake head, which is designed to provide a maximum of 0.15 meter per second of horizontal flow in order to avoid the impingement of sea life to the plant. Very large area of inlet covered with grids. And at the end of the brine discharge line, we have a special diffuser, as Tomer mentioned before, which is designed to improve the mixing of the brine with the bulk of the sea. So our plant occupies an area of 10 hectares. And is divided into 2 separate installations, each with half of the total capacity. The desalination process has 5 major steps. The first is the seawater intake and pumping station. From those 2 supply lines that we saw earlier, the seawater enters by gravity to the pumping station, then coarsely filtered and pumped to the next step. The pumping station is designed to work with 6 pumps in parallel and 1 in standby, a total of 7 and a capacity of 8,400 cubic meters per hour. The next step is the pre-treatment process. The pre-treatment consists of 2 filtration stages. The first is a dual media filter with anthracite sand filtration bed. And the second is 20 micron cartridge filter. After the pre-treatment, we have the RO desalination, which is divided into 2 steps, into 2 RO passes. The first pass is the SWRO, seawater reverse osmosis, and the second pass is the BWRO, which is brackish water reverse osmosis. Our RO has a unique design, a concept, which is 16-inch vertical pressure vessels and membranes, as opposed to conventional 8-inch horizontal installations. And there is a total of 16,400 membranes in the plant. You can see here the size of the membrane, how it is being loaded in the pressure vessel. The first pass of RO operates at a recovery of between 45 to 50% and up to 75 bar of pressure. and the second pass operates at a recovery of 95% and up to 20 bars of pressure. In addition, in the RO step, SWRO, we have energy recovery device by means of dual work exchanger, which recovers the energy from the high pressure brine with a recovery rate of 97%. The final step is the post-treatment and product water mineralization and chlorination, in which we achieve, according to the regulation, 80 ppm of hardness and 80 ppm of alkalinity. It is achieved by means of calcite bed reactors, and the reactor is stimulated by an addition of carbon dioxide and sulfuric acid. In addition, all the streams that are sent back to the sea, like the dual media filter backwash effluents, are being treated in a specialized facility to remove suspended solids and iron deposit. The treated water is sent back to the sea, and the sludge is being treated in inland disposal site. So in this facility, we are also actively cleaning the sea. Now I want to show you a short video of the erection process. Apologize, 1 second.
We did not see the video.
Oh, yeah. You cannot see the video?
Yeah.
Please try to make your PC duplicate so we see what you see. Right now it's on extend and we see the presenter view.
Mm-hmm. Okay. Can you see it now?
Yes, thank you.
Okay, and of course at 2014, the Sorek desalination plant wins the Global Water Awards for the desalination plant of the year. That is all. Thank you very much.
Thank you so much. And I'd like to give the floor now to Mark, who will moderate the Q&A session. And again, I would like to also apologize for the technical issues we dealt with, but that's part of our new era. Mark?
Thank you, Racheli. Yes, I saw a lot of very interesting presentations. So thank you all for sharing your the developments, innovations, and thoughts and ideas on the future. Maybe I would just like first to give the opportunity to give the floor to those who have questions themselves. I had some pre-prepared, but if there's any questions to the speakers, please either just unmute and put up your camera and ask them, or put them in the chat, or put up your hand digitally, whatever you think is easy. And if you need some time to think, I might use the time to ask Guido, because unfortunately, Guido, your presentation ended at the moment that it became very interesting, I think, where the electricity storage and the hydrogen storage was coming together into one system approach. And I think that would be also my question to you. Your company is moving away, it seems, or broadening from a system itself into a system solution. So not one part, but a system solution. Could you maybe share a little bit more on that as your presentation stopped at that moment?
Sure. No, thanks for giving me the opportunity. I had a wired Wi-Fi, wired connection instead of Wi-Fi to prevent this, and then it still happens. But anyway, so our company is moving forward towards large-scale production, because that will drive the cost down and increase the adoption rate of this technology, of course. But originally, we, as I said, we developed this for electricity storage as a dedicated battery. But now it turns out to have a nice bridging function. We are going to realize actually that concept. We are close to signing the contract for that. And recently we were in the news, maybe you noticed, with the deal with Vopak. I'm not sure if that was still on the screen. Vopak is, well, you know them as tank storage company. And you remember that a flow battery needs 2 large tanks. So if anywhere in the world you can build really extremely large flow batteries, it's on these seaport terminals. So that cooperation has been announced a couple of months ago. So that is really electricity storage, and the other direction that we are moving is integration with electrolyzers.
Thank you, Guido. And maybe so the way that your solution fits in the entire energy system, it allows like for balancing, grid balancing, etc. That's, I think, the ultimate goal, and then interfacing with different energy carriers.
Exactly.
Yeah.
So that's well, I'm still excited about it. It's a beautiful thing about this technology. As I said, it's called bycatch. I thought this was Dutch, but this is also in English, the word. But sometimes, you must be lucky, and you find this kind of unique applications. So no, you add different options to stabilize the whole system, instead of just adding a battery.
Thank you, Guido. I also see a question here from Ronnie to Tomer. How about the Hadera plant's specific energy consumption and water recovery rate? I think that also is a bridge towards the question I asked Guido, the integration of these things into the entire energy system. So how about the integration of this specific Hadera plant, Tomer, but the integration of desalination into an energy system as a whole? Are there any thoughts on the future developments there? I don't see Tomer in the meeting anymore. Is he still there? Maybe this is something otherwise, Slava, you could maybe say something about.
Well, I think in all that we have seen today is the costs are probably the most important points. That we didn't see many numbers, but basically I think this is going to be probably the main issue. For instance, I know that let's say blue energy, the costs and the outputs per unit area are very critical factors there, and I think this will make it go eventually compared to other technologies. And I actually have a question connecting two different things. So the question about connecting blue energy with the brine disposal that Tomer was highlighting. So is using brine, can be versus, for instance, seawater or maybe wastewater, which is relatively low salinity, or maybe treated wastewater, can be a source of energy and probably recovery. And so it can kill two birds. Dilute the brine, first of all, which is anyways done today, and eventually, and also produce some energy. So it can kind of compensate for the energy consumption of the desalination plant and give back some energy. Is that
again bycatch?
It's feasible.
Yeah, it's again a bycatch. But Pijn, can you say something about this?
Well, yes. In fact, that was one of the slides I showed about potential configurations to combine seawater and treated wastewater with RO system and including an RED system that catches both fish. Because if there is a great enough salinity difference, blue energy can be generated. And also the discharge, the salinity level of the discharge can be reduced. So we see this as a very promising configurations. Yeah.
Thank you. You're on mute, Slava.
Yeah. Is it possible to make specific estimates? Let's say using a desalination plant brine, which is highly saline, so probably the efficiency could be much higher than in the case of a dam that you're working on, and actually the salinity of the sea is much lower, as far as I know, than what we have in the Mediterranean, and so if it's brine, it's even twice as saline, and so the efficiency could probably go up and become economic, and the whole process can become economic if cooling water of the nearby power plant is combined with the brine of the desalination plant. So it will be interesting probably to see the numbers and have some economic estimate.
Yeah, this is of course still in an early stage at this moment. So let's say we're working on these configurations and do at least calculations and obviously some tests in, let's say, the specific parts of the configuration. But yeah, definitely, you're absolutely right in this perspective. We hope to have to have these results in practice as well.
Thank you, Pijn and Slava. I think I see already very nice bilateral opportunities arise here across borders. So I'm really happy with that. I see there are more questions coming in. Unfortunately, we are really running out of time. Apologies for the technical difficulties. I think I would like to give the floor to Racheli, and I think she will also announce opportunities for you guys to reach out to each other to follow up on these specific questions and collaboration opportunities. Thank you all.
Yeah, thank you, Mark. So indeed, we're about to conclude, and it's good that there is room for more questions, because that's what we actually want. We want to create a dialogue. After we will end our session, we will circulate the presentations, and you can interact with each other, of course, and hopefully in that way start new collaborations. But I also hope is that what we showcase today is that when we look at the clean hydrogen sector, that introducing technology, which is very ripe on other ends, such as water desalination or membrane technology, is indeed ready for the future of the hydrogen production. And therefore, we welcome all of you to continue thinking also along those lines of where are new disciplines that are needed in order to address the challenge of producing green hydrogen and contributing to climate change and sustainability. So I'd like to thank all of you, and I wish you a very good day and hope to see you soon, and we'll be in touch. Thank you so much.
Thank you. Thank you very much. Thank you.
Many thanks.
Thanks a lot. Bye-bye.
Bye-bye.